Hello and welcome back to episode 7 of Calculus 1. I am Mohammad Momenzadeh, and today we will discuss about the derivative, the most important topics in the Calculus 1, one of the most important indeed. This topic somehow surrounded us, and we can see the footage of this derivative everywhere in around of us in a reality. So let us take a look at that concept clearly and see that what does it mean. So the topics that we have it, as I said it before, it's a basic definition and derivative and rate of a growth, and some relation will be discussed. So let us start our discussion by take a look at one picture. So in this picture you can see one of the things that is happening around of us, means that the movement. The derivative is related totally to the movement, to the growth, to the changes in everything. And as you know, if you are alive and you just live in a reality, you can see that everything is moved step by step or gradually. So over here I consider one tree. It started by the first day. This timeline determined in a horizontal line. You can see that the time is considered as a horizontal line, and this is the first day of consideration of that tree. So at the first day you can see that the tree has this height, and this height is changed and is growing up to this stage at the day, for example 5 or 10. Let us put it 10, the day 10. The 10th day we have this height, and at the end it's growing up step by step, and you can see that, for instance, at the day 30 we have this height of a tree, and at the end, at the day of for instance at the day of 40 we have this height of a tree, and the y line over here determine the height that we have it. So we can use this concept, the concept of the changes, the concept of movement, the concept of any kind of the modification in around of us. We can make them by one diagram. So over here I just choose the tree because it's more reliable and more sensible for the person to understand these topics. So we can start our discussion by talking about the movement of a car. We can talk about the population of rabbits in one island. So we can talk about a lot of things. But let us connect these heights together to have a diagram of a growth over here. So if I consider the the growth of this tree, we can see the diagram of the growth is going like this. I mean, it's going up like this, and we have this type of the height over here. Now the question that we have it is about the rate of a growth over here. If I denote the first point as a x0, the second one as a x1, and so on, means that the height of a tree in each stage is determined by one value of x. So we have 4 value of x over here. And right now, if I want to know that what's happened between x1 and x2, means that I want to know that how much the tree is growing between this duration. So if I want to write it, then I can say that the rate of a growth over here is equal to the differences of heights over there that can be determined by one ratio. So let us write that ratio over here. So we can write it like this. I mean, we may use this ratio and write over here the rate of a growth based on that stage. So you can see that it's going to be the x2 minus x1, the differences between their heights over the time that we have it. So the heights, I just use the y for the heights. Let me just use the y for that concept. So we have y2 minus y1, and for the time that we have it, we use the x. So over here right now, simply we can calculate that rate of a growth by this calculation. Means that right now, if the second highest over here determined by y2, as I said it over there, this one is determined by y2, and the initial highest over there is determined by y1. So let me just put y1 for the initial value. Then the differences between them determine that how much the tree is growing up, but it's important to consider it in a duration of a time, so I divide it by x2 minus x1. For instance, if it's growing up 4 inches, for example, let us write it 4 inches, and this duration, as you can see over there, is 20, then I can say that the rate of a growth for that tree is 4 inch over 20 days. So we have this actually rate of a growth for this tree. It's important to understand that the main factor over here that determine this rate is very important here, and by knowing that rate we can predict the future of this growth. For instance, for the next step we can predict that how much we should expect it to growing up, or if it's gonna be less, we realize that at this stage that rate decreased. So over here, by this type of the discussion, we can see that how can we calculate the rate of a growth for this case, for that simple case. However, we can talk about the distance, the population of some species, for instance, in some occasion, and by calculating this value we evaluate indeed the rate of a growth, or the value that determine the changes in that parameters. So over here we calculate the rate of a growth by subtracting the y from each other. We can use one symbol for this subtraction. We use the delta y, this symbol, to determine the differences of a y. This delta is a capital D in a Greek alphabet, and it's coming from differences. The delta y determine the differences of a y values, so it's gonna be y2 minus y1, and the delta x determine the differences of x values. So right now delta x also is denote the x2 minus x1 in this case. So means that by the another word we can write this rate of a growth as a delta y over delta x. So right now let us consider one diagram for the case that the tree is not our consideration only. It can be consider any type of the growth. So in this case let us see that how can we calculate the rate of a growth, and if we can evaluate the instant rate of the growth or instantaneous value for the rate of a growth. So let us take a look at that diagram right now. So at this stage I sketch one diagram for one arbitrary function. I consider the function as y equal to fx. It could be considered as a rate of growth for the tree growing, or it can be considered a population, or any type of the diagram can be considered over here. Right now I want to know that what's happened in a rate of a growth at a given point A. To know the rate of a growth I need 2 points, not only 1 point, because I cannot calculate the changes for 1 point at one moment. So for this reason, I choose 1 point close to the point A, and I denote that point by A plus H. So this point is close to that given point A. So the heights over here determine the value of f at that point. For instance, this dashes determine the f of A, or the heights of the diagram at the point A. And if I consider the neighbor of A as a plus H, then this black dashes over here determine the f of A plus H. So right now I have two heights, and I can calculate the similar value or ratio for this case as well. So if I just take a look at this part closely, means that if I just make this part bigger and take a look at that one again over here, let us just put over here the situation that we have it. So if I consider the situation that we have it over there, then we have something like this. I mean, at this point, at that case, at one side we have a point A that we denoted over there, and we have one height that the height over there determined by f of A. So let me just write it f of A, and I have one neighbor of A as well that I denoted by A plus H. This point could be considered at the left side of A as well. Doesn't matter that it's going to be right side or left side, so I just put it at the right side because it's easier to sketch it. So this point is A plus H. I mean that this H could be a negative value, not only the positive value should be considered. So it will be f of A plus H, the height at that point, and the differences between them can be considered over here. This is the diagram of y equal to f of x, and right now I can determine the differences of this value as well. Means that the differences between these heights can be evaluated by this actually segments that I denoted by delta y. So this delta y denote the differences between the y value, which is equal to f of A plus H, the second highest that we have it at that point, minus the f of A, which determine the value of highest at the point A. And on the other side, you can consider the differences of x values as well. This is the differences of x values that we have over here, delta x, and this delta x is equal to h over here, because this is the differences between A plus H and A. So let us make that ratio over here. Means that we had a ratio that determined the rate of the growth at that point. Means that this ratio evaluate the rate of growth. So I hope that you can see that word. So let me just make it like this. Okay, rate of a growth is here, and as I said it, we use this ratio that determine the delta y over delta x, delta y over delta x. And if I just make that ratio over here, then it will be f of A plus H, f of A plus H. This is the second value of y minus the first value, which is f of A, and I should divide this value by the differences of x's over there, or the x values, which is equal to h. If I consider A plus H at the left side of A, then by having the negative value for the delta x at the denominator, we reach to the same fraction. So this fraction, this ratio that we have it over here, determine the rate of a growth. But if I want to calculate that one at one moment, at the moment that is happened, means that at the point A, then I should tend that a plus h to the a, or I should tend h to the 0. So if I want to just move this point from a right side to the point A over here, then it's enough to tend h to the 0. Then I will find the value of a derivative at the point A. By the another word, the derivative of a function, so I can write it over here that the derivative of y equal to f of x at x equal to a, that we should find one symbol for that one. It's worth to denoted by one symbol. So this derivative is denoted by f prime. We use this notation. We put a prime at the top of f to determine the derivative. So f prime at the point A will be equal to the limit of that ratio. It will be equal to the limit of that ratio that we had it. So this is the limit of that ratio where h is tending to 0. So we should have this ratio as well should be replaced here. So right now we found the value of a derivative at the point A, and in this way we can calculate the derivative of that one, and it's determine the instantaneous rate of a growth. It's determine the changes at the moment. So right now there are a lot of things that we can consider it for this value. For instance, if I just connect these 2 points together, then by connecting these 2 points together, I can construct a right triangle. So you can see that it will be a right triangle over here. And if I consider this angle as an alpha, then delta y over delta x, as you remember, that determine the tangent of alpha. By the another word, we have tangent of alpha equal to tangent of alpha is equal to delta y over delta x, because it will be the opposite side over adjacent. So the opposite side is delta y and adjacent is delta x. So by the another word, this derivative that we calculated is a limit of a tangent of alpha, and it's determined over here the value of a derivative. What does it mean? Means that we have the slope of a line over there. So let us take a look at that concept closely as well. So the satisfaction discussion about the slope of a tangent line needs to have a good information about the line and the attitude of a line in the two-dimensional space. I know that most of the student has this background in high school about the line and the slope of a line and some related issues, but it's not a bad idea to have a quick review about the concept of the line. So if you consider a straight line in a two-dimensional space like the line that I just sketched over here, then we have some property which make the line unique. And as far as I remember, in a Thomas book, the calculus book of the Thomas, one chapter totally belongs to the discussion about the line. That much this concept is important. Indeed, the human try to simplify the real phenomena by some concepts. So the easiest way to model the real phenomena is making the linear forms of the construction. And as much as this system is simple, you can decide about it easier, and you can expand and somehow develop this type of the model to the higher complicated or more sophisticated cases. So if you have a line, you can see a line over here, then there is one unique property of a line, that the slope of a line or the changes inside of the line is totally invariant through the way that we travel in a line. By the another word, this slope, this changes over here is not change in any part of the line. So for this reason, we can simply find the equation of the given line. So if I have a line and I consider one point over this given line, let us name that point as x and y. When we discuss about the formula of a line, means that I'm looking for a relation between x and y such that all points like x and y which totally lay on a line has that property. For instance, this x and y which is lay on a line, it should have some property that make it unique, and we discuss about that type of the properties. By the another word, when we consider a point like x and y over the line, there is some relation between the first component and second component of that point, and we are looking for that relation over the given line. If I consider 2 points in a space, then I can make one actually unique line that passes through that to a specific point. Let us name these 2 points over here as A and B. So if I have the point A and B, then from these 2 points we have a unique line that passes through these 2 unique points. So let us name the first point as a x node and y node, and the second point let us call it by x1 and y1. So this is the component of A, and the second component is given by x1 and y1. So by having 2 points of a line, we can find the slope of a line as well. Means that we can construct one right triangle over here as well. And in this right triangle, you can see that the angle that we have it over here is alpha. So I can denote this one by alpha. Then this alpha and also this alpha over here are the same. So we have the same alpha over there. So the opposite side of the alpha determine the delta y, or the differences between the y value, and the adjacent of this right triangle determine the delta x. And as you can see over here, in this given line that we have it over here, we have the following things. The slope, or the gradient of this actually a straight line can be calculated as the differences of y values, or delta y, which can be calculated as y1 minus y0 over the delta x. And this value, the slope, is constant for all values over the line. And as you can see, this delta y over delta x can be calculated as a tangent of alpha. Means that if that straight line make the alpha, the angle alpha with the horizon of the space, then the tangent of alpha determine the slope or gradient of this straight line. So because the slope is constant through the line, then I can define the another slope as well. We can use the point of x and y, one arbitrary points over the line, and the point A as well, to determine that slope. Then this delta y over delta x can be written as y minus y node, and divided by x minus x node. So this value also determine the slope, and as I said it, through the line the slope is constant, so I can write that one as the value that we denoted by m, or the slope of a line. From here we can find the line equation, means that y minus y node is equal to, if I multiply both sides by x minus x node, then I reach to that formula for the line equation, m times x minus x node. So right now we have the straight line equation. So let us take a look at the graph, the situation that we have it here. So as you can see over here, I just sketch one line, y equal to minus 3x plus 3, and you can see that the point over here is given by this component that I just push it over here. So you can see that the relation between all of these points is as follow: minus 3x plus 3 is equal to y. For instance, if I consider one point, one simple point like 1 and 0, if you multiply the x over here, which is 1, by minus 3 and add 3 to that value, the result will be 0, that you can see over here. Or if you consider the point like the value that we have it over here, like 0 and 3, then you can see that by substituting x by 0, the value of y will be 3. And this slope is negative because it's decreasing and coming down over here if we just travel to the positive side of the horizon. So right now let us take a look at y equal to fx, and let us determine this slope of a line for the given 2 points over here. If I consider 2 points, for example the points A at this position, let me just mention it here, okay, and the another point at this position, that is a plus h1, and I connect these 2 points by one straight line to each other, then let us calculate the slope of the line for this case. Let me just put it over here to have the better situation. Okay, so right now if I want to calculate the slope of this line, it can be calculated easily. So why? Because we have the component of the given point, means that at this point the component of the given point is a. The first component is a, and the second component is a value of a function at the point a, so it will be f of a. For the second point that I mentioned it over here, we have this component a plus h1 is a first component, because we have the first component as a plus h1, and the second component is given as a f of a plus h1. A plus h1. So this is the component of the second points over here. Right now, to calculate the slope of that orange line over there, we can say that the slope over there, that we can denote it by m again over here, or it's better to label it and have the m1 over there, should be calculated as a delta y over delta x. And if I just write the ratio for delta y over delta x, then I have the following expression, means that I have delta y over here as f of a plus h 1 f of a plus h1 minus this is the second value of y minus the first value of y, which is given at the point a, f of a, and I should divide it by the differences of the x values, and the x values, the differences between a plus h1 and a is h1. So this will be the slope of m1. And if I continue this line as well to the horizon, means that if it continues over there, it's a bit longer than I expected. So by comparing the angles over there, it's enough to put the horizon over here have the horizon like this, so these two gonna be parallel. Right now you can see that this angle over here can be considered as this value. This angle over here is given by alpha, and this tangent of alpha determine the value for that actually slope over here. So because this alpha is greater than 90 degree, the tangent of alpha will be negative, and because of that the line will be decreased, as you can see over here. So let us examine the value for the second points that we mentioned it over here, means that for this point at this position. So if I connect them together, then I have a positive angle. So let me just connect these 2 points. So you can see that the value of that angle is positive, means that if I consider it over here and sketch the horizon again at this stage, so the horizon is gonna be like this. Right now the alpha that I have it over here is less than 90 degree, and where it's less than 90 degrees, so the value will be positive. The tangent of alpha will be positive. So by comparing these two values, I can evaluate the slope at the second point over there as well. Means that the slope where I choose that another points on the graph of a function, and if I denote it by m2, then it's similar to the previous fraction. It's equal to f of a plus h2 minus f of a over h2. And the reason that I construct the slope for that that type of the tangent line over here is evaluating the slope at the end of the day when we have the tangent line. What does it mean, the tangent line? This will be a tangent line at the point A, and as you can see, this slope is closer to the green line than the orange line, and it seems that the slope of that tangent line means that at the end of the day, this is the conclusion that I want to reach to that point. The slope of tangent line, if I just write it over there, the slope of tangent line, the line that is tangent to the given graph, can be calculated as a limit of that values, and the limit of that values determined by the f prime or the derivative at the point A. So this is the another meaning of the derivative when we have a function and graph of a function is given like this. So right now we get some information about the derivative. We understood some concept about the derivative. Right now it's a time to discuss about the technique of a derivative. Let us take a look at some technique of the derivative. So before that, we're going to the technique of the calculating derivative. It's not a bad idea to calculate the derivative of fx equal to x squared, one simple polynomial function, that parabola, by using the definition of the derivative. So if we want to calculate the derivative of this function or f prime at the arbitrary point of x, then we can use the formula that we have it. So based on a formula, this f prime is equal to the limit of some fraction. If you remember that, it's going to be limit of h tending to 0, and that slope should be written over here, and the slope over here is given by f of x plus h, minus f of h. This is the differences of y or delta y minus f of x, and divided by h. And if I just substitute the corresponding value for this fraction, then this limit is changed to this form. So the first line determines the definition of a derivative. So instead of f of x plus h, I should substitute the value of x plus h instead of the x over here. So f of x is x squared, so f of x plus h will be x plus h squared. So I will write over here x plus h squared, and instead of f of x, again I should write x squared. Let us write the x squared over here and divide it by h when h tending to 0. When you want to calculate the limit, the first thing is substitution, and if you substitute it, you realize that this is 0 over 0, the undetermined form of 0 over 0. So because it's a polynomial, so it's a good idea to use some identity, some algebraic identity to calculate the limit. So if you take a look precisely at the numerator of this fraction, you will see that it's a conjugate state, means that the first one is square, a square minus b square. So I can rewrite that expression as follow. I can rewrite it as x plus h minus x, x plus h minus x, and next time I should write it as plus x. So the another one is, as I said it's gonna be x plus h plus x. So I will write it over here x plus h, and this one is plus x, and these terms are divided by h. And as you can see, x minus x will be cancelled, this x and x will be cancelled, then I have h times this expression. So if I rewrite that one again over here at the bottom, so instead of this expression, I can rewrite the value, corresponding value over there, that is equal to h. And right now this h also can be cancelled by the denominator. The 0 factor is cancelled, and right now just put h equal to 0 at that expression, and if I put h equal to 0, then x plus x give us 2x. So we found the first derivative, means that the derivative of this function fx equal to x squared is 2x. Indeed, this 2x determine the slope of a line for this given graph. For instance, at the point 0, the derivative is 0, because 2 times 0 will be 0. So if you sketch the tangent line at the point 0, you will see that the tangent line determines the 0 value of the derivative. And if we're going to the right side of this graph, as you can see, the slope of this line is positive. So if I consider this situation, as you can see, wherever I put the tangent line, the slope of that line is positive. It can be seen by the angle that we have it over here. The angle over here is less than 90 degrees, so that type of the derivative at the right side, where x is positive as well. But at the left side of this parabola, for example, over here, if I sketch the tangent line, you can see that the tangent of this angle, which is more than 90 degree, is negative, and because of that the value of a derivative at the left side is equal to 2x, and x is negative, so the result will be negative as well. So at the first step, I just write the first rule of the derivative over here, which is too important, and most of the rules that we have it is constructed by using this formula. Means that if we have a function fx as x to the power of n, then the derivative of that one will be n times x to the power of n minus 1. Means that that number n is coming down and is coming close to the number x, means that it's coming over here, and we subtract 1 from that value as well to evaluate the derivative. Let us calculate the derivative of x cubed. If I have x cubed and we want to calculate the derivative of x cubed, then that number 3 is coming down. I have 3 times x to the power of, right now 3 is an exponent. I should subtract 1, then it's going to be a square. So we have 3x squared. For the next case, when we have x to the power of 4, the derivative of x to the power of 4 will be 4 times x to the power of 3, or x cubed. So as you can see, we subtract the exponent again 1 times and we have x cubed. For x to the power of 7, we have 7 as a number which is coming out, then x to the power of 7 changed to x to the power of 6. This rule is valid for the negative exponent. For example, if I have x to the power of -1, this -1 is coming out. I have -1 times x to the power of, right now I should subtract 1 from the exponent. -1 minus 1 will be -2. Don't make the mistake to make it 0. So you should subtract 1 from that exponent. So -1 minus 1 will be -2. So the next one is x to the power of -2. If I want to calculate it, then -2 is coming out. I have -2, then x to the power of -3. I subtract 1 from the exponent again. So then minus x to the power of -3, if I want to calculate the derivative, is -3 times x to the power of -4, because I subtract 1 from the exponent. So it's help us to calculate the derivative of the expression, which can be written as a fraction. For instance, if I have x 1 over x to the power of 5 and I want to calculate the derivative of that expression, then to calculate that derivative, it's not a bad idea to push that x5 to the numerator. Means that I can rewrite that one as x to the power of -5 and then take a derivative. Right now you can calculate the derivative easier. So by just taking the derivative from this expression, we have -5. Right now we can take out -5 and write it as a -5 x to the power of -6. And even you can simplify it more than this, because the exponent is negative. You can rewrite it in a denominator and write it as a -5 over x to the power of 6 to have the positive exponent when you just write it like that. So for the fraction also we have the same thing. Means that if you have a fraction, we can use the same formula. Means that, for example, x to the power of half is coming out. Right now x to the power of half minus 1, which is -half. So we can calculate that expression like this as well. Or x to the power of 2 over 3. This 2 over 3 is coming out. Right now I should subtract 1 from the exponent. The exponent is 2 over 3. If I subtract 1 or 3 over 3 from 2 over 3, the result is -1 over 3. So we have the same situation for the next example. 3 over 5 is the exponent of x. I just write it over here as a coefficient. Then x to the power of 3 over 5. 3 over 5, I subtract 5 over 5 or 1 from the exponent, then the result is -2 over 5. By the another word, this formula can help us to calculate the derivative of roots as well. For example, if I have x, the roots of x cube with the fourth roots of x cube, for example, if I have fourth roots of x cube and I want to calculate the derivative of that one, first of all, I change the exponent of that roots to the fractional exponent. Means that I can rewrite it as a x to the power of 3 over 4, because the exponent can be written like this. So right now I can calculate the derivative. The derivative will be 3 over 4 as a coefficient. This number is coming out, and then x to the power of 3 over 4 minus 4 over 4, or 1, which is -1 over 4. And even you can simplify that expression more. means that you can make the exponent positive by converting that expression to the denominator and rewrite it as 3 over 4 times x to the power of 1 over 4, the positive exponent. And then this 1 over 4 also can be interpreted as a root, means that I can rewrite it as 3 over 4 x to the power of 1, and that 4 at the denominator of exponents will come out inside of the roots, and we have 4 roots of x to the power of 1. So in the next lecture we will discuss about this type of the things and the exponent more than this with the details. So I hope that you understood the concept of the derivative, which is one of the most important thing inside of the calculus. Thank you for your attention.